This is the video for Part 1 of Section 7.1, Definition and Examples of Groups. So far in the course, we've been looking at rings. In this chapter, we want to examine another important algebraic structure, that of a group. A group is an algebraic system with a single binary operation. While the definition of a ring is abstracted from the properties of the integers, the definition of a group is abstracted from the properties of sets of permutations. So we'll start with the definition of a permutation. Let T be the set consisting of the integers 1, 2, up through n. A permutation of T is a one-to-one correspondence or bijection from T to itself. Suppose f from T to T is a permutation. We can write f in any of the following forms. First, we have function form, where we just indicate each image of the elements in the set T. So f of 1 is a1, f of 2 is a2, and all the way down to f of n is a sub n. Second, we have arrow form, where we basically just use arrows to indicate the images. So f maps 1 to a1, 2 to a2, and down to n to a sub n. And finally, two-row form, which is the form we'll be using most of the time. And in this case, we write f as a 2 by n matrix, where we have the entries 1, 2, up through n in the first row, a1, a2, down to a sub n in the second row. So the top row contains the elements of T, and the bottom row the images of the elements. For an example, let's list the permutations of the set T equal 1, 2, and 3. So in this case, n is equal to 3. First note that there are 3 choices for the image of 1, 2 choices for the image of 2, and 1 choice for the image of 3, for a total of 3 times 2 times 1, or 6 permutations. Since a permutation is a one-to-one correspondence from the set T to itself, we're not allowed to repeat any images. So first we have the permutation 1 maps to 1, 2 to 2, 3 to 3. Second, we have 1 maps to 2, 2 to 3, 3 to 1. Third, 1 maps to 3, 2 to 1, 3 to 2. Fourth, 1 maps to 2, 2 to 1, 3 to 3. Fifth, 1 to 1, 2 to 3, 3 to 2. And finally, 1 maps to 3, 2 to 2, and 3 to 1. And these are our 6 possible permutations of the set 1, 2, and 3. Next, we want to show, let's let S sub 3 denote the set of permutations of the set 1, 2, and 3. We want to show that the set of permutations in S3 satisfies the following properties under the operation of composition. First is G1, closure. For all f and g in S3, f composed with g is an element of S3. G2 is the associative law. For all f, g, and h in S3, f composed with the composition, g with the quantity g composed with h, is equal to the quantity f composed with g composed with h. G3 is existence of an identity element. There exists an element I in S3 such that for all f in S3, f composed with I is equal to f, and I composed with f is equal to f. And G4 is existence of inverse elements. For each f in S3, there exists an element f inverse in S3 such that f composed with f inverse is equal to the identity element, and f inverse composed with f is equal to the identity element. So we'll start with G1, closure. For all f and g in S3, f composed with g is in S3. So let's suppose that f and g in S3 are arbitrary permutations. That is, f maps t to t and g maps t to t, and they're both bijections. Their composition then maps their composition f composed with g maps t to t. And since the composition of 2 bijective functions is bijective, then f composed with g is also a bijection. Therefore, f composed with g is an element of S3, and G1 holds. For instance, let's suppose that f is the permutation mapping 1 to 3, 2 to 2, and 3 to 1, and g is the permutation mapping 1 to 2, and 2 to 1, and 3 to 3. We can compute the composition f composed with g, say using the arrow form of the permutations. So let's start by writing out g. So g maps 1 to 2, 2 to 1, and 3 to 3. And then we'll apply F to each of the images. So F maps 2 to 2, 1 to 3, and 3 to 1. So then the composition is going to map 1 to 2, 2 to 3, and 3 to 1. We can also use the two-row form of the permutations directly to compute their composition, and this is usually the most convenient way to compute compositions. Now remember that in composing two functions, we apply the function on the right first and the function on the left second. So F composed with G is the composition shown, and we can start by writing out the first row of our two-row form for the composition, so just indicate 1, 2, and 3. And then let's look at what each of the elements 1, 2, and 3 map to under the composition. So first off, in G, 1 maps to 2, and in F, 2 maps to 2. So in the composition, 1 maps to 2. Then in G, 2 maps to 1, and in F, 1 maps to 3. So in the composition, 2 maps to 3. And then in G, 3 maps to 3, and in F, 3 maps to 1, so in the composition, 3 maps to 1. And so there is our composition. Next, let's look at G2, the associative law. So let's suppose that F, G, and H are arbitrary permutations in S3, and we need to show F composed with the quantity G composed with H is equal to the quantity F composed with G composed with H. Now to show this, we need to show that for each element I in our domain, when we apply the function on the left to I, we obtain the same result as when we apply the function on the right to I. The way we prove that two functions are equal is we show that when we apply them to each element in the domain, we obtain the same result. So let's suppose that I and t is arbitrary. Then the left side will be, so in this composition, this will be F composed with the quantity G composed with H of I. And then inside the parentheses, G composed with H of I will be G of H of I. So the result will be F of G of H of I. The right side, this time we'll apply H to I first. So this will be F composed with G applied to H of I. And then this will be F of G of H of I again. So the two sides are equal, and thus the equality holds, and therefore the associative law G2 holds in S3. Now note that since we never used the fact that the functions were permutations, just that they are functions, this proof actually shows that the composition of functions in general is associative. Next, G3, the existence of an identity element. So let's start by choosing I to be the permutation that maps 1 to itself, 2 to itself, and 3 to itself. And let's suppose that F is an arbitrary permutation in S3 where F maps 1 to A1, 2 to A2, and 3 to A3. Then for each I equal 1, 2, and 3, if we apply the composition F composed with I to little I, this will be F of capital I of little I, and capital I maps each element I to itself, so this will be F of I, which is equal to A sub I, which is equal to F of I. And then I composed with F applied to little I, this will be capital I applied to F of I, which is equal to I of A sub I, which is just equal to A sub I, which again is equal to F of I. So this proves that F composed with I applied to I is equal to F of I, and I composed with F applied to little I is also F of I. And therefore, F composed with capital I is F, and capital I composed with F is F. And thus, the permutation I is an identity element for S3, so G3 holds. Finally, we have G4, the existence of inverse elements. So let's suppose that F from is an arbitrary permutation in S3, then F is a bijection, which implies that its inverse, F inverse, exists. And if we suppose that F is the permutation that maps 1 to A1, 2 to A2, and 3 to A3, then written in arrow form, we have F as shown. And the inverse function will be given by, so the inverse undoes what F does, so the inverse function F inverse will map A1 to 1, A2 to 2, and A3 to 3. And then for each I equal 1, 2, and 3, F composed with F inverse of A sub I will be F of F inverse of A sub I, and F inverse of A sub I is just I, and then F of I is A sub I, which is equal to the identity applied to A sub I. And F inverse composed with F of I is equal to F inverse of F of I, which is equal to F inverse of A sub I, which is equal to I, which is equal to the identity capital I applied to I. And therefore F composed with F inverse is equal to I, and F inverse composed with F is equal to I, and thus G4 holds. So this shows that S3 satisfies our four properties, G1, G2, G3, and G4. And we want to abstract the properties of S3 to obtain the definition of a group. So for our definition, we say that a group is a non-empty set, capital G, equipped with a binary operation, which we'll denote by star, that satisfies the following axioms. First is G1, closure, for all A, B, and G, A star B is in G. Second, G2 is the associative law, for all A, B, C in G, A star, the quantity B star C, is equal to the quantity A star B star C. G3 is existence of an identity element. There exists an element E in G called the identity element, such that for all A in G, A star E is equal to A, and E star A is equal to A. And finally, G4 is existence of inverse elements. For each A in G, there exists an element D in G, which is called the inverse of A, such that A star D is equal to the identity E, and D star A is equal to the identity E. Now a group is said to be abelian, provided it also satisfies the additional axiom G5, which is the commutative law. For all A, B, and G, A star B is equal to B star A. A group which is not abelian, that is, which does not satisfy the commutative law, is called non-abelian. The term abelian is in honor of the early 19th century Norwegian mathematician Niels Henrik Abel, who is best known for showing that the general quintic equation is not solvable by radicals. The preceding example shows that S3 is a group under the operation of composition. However, S3 is not an abelian group. To show this, we need to show that S3 does not satisfy axiom G5, the commutative law. If I let F be the permutations 1 to 3, 2 to 2, 3 to 1, and G be 1 to 2, 2 to 1, 3 to 3. Now we showed earlier that F composed with G is the permutation mapping 1 to 2, 2 to 3, 3 to 1. However, if we compute the composition in the other order, G composed with F, this will be 1 maps to 3, 2 to 1, and 3 to 2. And we can see that F composed with G is not equal to G composed with F, and thus S sub 3 is not abelian. In general, the set S sub n of permutations of the set 1, 2, up to n is a non-abelian group under the operation of composition. S sub n is called a symmetric group on n symbols. Now, when permuting the elements of T equal 1, 2, up through n, there are n choices for the image of 1, n minus 1 choices for the image of 2, and so on down to 2 choices for the image of n minus 1, 1 choice for the image of n. So there are going to be n times n minus 1 down to 2 times 1, or n factorial permutations in S sub n. As another example of a group, we consider the symmetries of a geometric object. Let's let capital omega represent a square with corners labeled 1, 2, 3, and 4, as shown. A symmetry of omega is a motion in space which carries the square into itself. If we visualize the square as a cutout piece of cardboard, if you pick up the square, rotate it counterclockwise by 90 degrees, and then set it back down, the square will occupy the same space. The individual corners, however, will be in different positions. So corner 1 will be where corner 2 was, corner 2 will be where corner 3 was, corner 3 where corner 4 was, and corner 4 where corner 1 was. So this 90-degree rotation is one example of a symmetry of the square. As another example, starting with the original square, if you pick it up and rotate it by 180 degrees about a horizontal axis passing through corners 1 and 3, and then set it back down, the square will again occupy the same space. This time, corners 1 and 3 will still be in their original positions, but corners 2 and 4 will have switched positions. This symmetry is called a reflection about the horizontal. So if you imagine starting with the original square and reflecting it about the horizontal axis, we'll obtain the square shown to the right. Now, note, even though we call this a reflection, it's really another rotation, but this time the rotation is out of the plane of the square. Altogether, there are 8 symmetries of the square. We can start with a rotation by 0 degrees, which is really doing nothing, a rotation by 90 degrees, as we saw, a rotation by 180 degrees, this is a rotation in the plane of the square, and a rotation by 270 degrees, again in the plane of the square. And the rotations are all taken in the counterclockwise direction. And then we have 4 reflections. We have the reflection in the x-axis, a reflection in the y-axis, or about the vertical. We can reflect about the line y equal x, and we can reflect about the line y equal minus x. Now, since each symmetry carries the square into itself, the result of applying one symmetry followed by another will also be a symmetry. That is, the composition of 2 symmetries will be a symmetry. For instance, suppose we apply the 270-degree rotation R3. So starting with the original square, after we apply the rotation, we obtain this square, followed by D, which is the reflection in the x-axis. We'll obtain the square to the right. Now, comparing this with our 8 symmetries, you'll see that the result is the same as applying H, the reflection about the line y equal x, which means that D composed with R3 is equal to H. Now, again, recall that when we write out compositions, the function on the right is applied first, and the function on the left is applied second. So D composed with R3 means apply R3 first, followed by D. Now the set D4 of our 8 symmetries is a non-abelian group under composition, and it's called the dihedral group of degree 4. To verify this, we need to show that D4 satisfies the 4 group axioms. Now, the discussion above indicates why D4 is closed under composition, so G1 holds. So if we apply first one symmetry followed by a second symmetry, the result will be another symmetry. The associative law holds for all functions under composition, so G2 holds in D4. The rotation by 0 degrees, R sub 0, is an identity element, so G3 holds. And each element in D4 can be shown to have an inverse element. For instance, R1 inverse, that's the rotation by 90 degrees. R1 inverse will be R3, the rotation by 270 degrees. R2 inverse, R2 is the rotation by 180 degrees, and it's going to be its own inverse. And R3 inverse will be R1. And each reflection will be its own inverse. So all 8 of our symmetries have an inverse element, and therefore G4 holds. Now, just as we computed the composition D composed with R3, we can compute all possible compositions to obtain the operation table for D4. And that's as shown. Now, the entry F composed with G in the table appears in the row corresponding to F and the column corresponding to G. So, for instance, the entry for D composed with R3 appears in the row corresponding to D and the column corresponding to R3. And that will be H. As another example, let's let capital delta represent an equilateral triangle with corners labeled 1, 2, and 3 as shown in the diagram. The dihedral group of degree 3 is the group of symmetries of this triangle, again under the operation of composition. So for an equilateral triangle, there are 6 symmetries. We have a rotation by 0 degrees, which is again doing nothing. R1 is a rotation by 60 degrees. Again, we're going counterclockwise. R2 is a rotation by 120 degrees. And then we have 3 reflections. We can reflect about the horizontal or the x-axis. We can look at the reflection about the line y equal minus square root of 3x. So that's a line that makes a 120 degree angle with the x-axis. And we can look at the reflection about the line y equals square root of 3x. That's a line that makes a 60 degree angle with the x-axis. Now the symmetries of any geometric object, including three-dimensional objects, will form a group under composition. Symmetry groups have important applications in many areas of science, including crystallography, chemistry, and quantum physics. One of the main ways in which groups are classified is according to the number of elements in the group. And this leads to the definition of order. A group G is said to be finite or of finite order, provided that it has a finite number of elements. In this case, the number of elements in G is called the order of G and is denoted G with vertical lines on either side. A group with infinitely many elements is said to have infinite order. For instance, the symmetric group S3 has order 6. In general, the symmetric group S sub n on n elements has order n factorial. And the dihedral group D sub 4 has order 8.